I welcome everyone to this video. It's a very important one. We're going to prove this limit. Many of you have seen this. Limit as theta approaches 0, sine theta over theta equals 1. That theta could easily have been replaced by a variable x. Limit as x approaches 0, sine x over x. You know, when you've seen this, we're used to solving this in a particular way. You'll do the derivative here of the numerator, you'll do the derivative of the denominator, you'll have cosine theta over 1. When you put in here a 0, you have cosine of 0, which is equal to 1. You arrive at the end result, but here we are applying the L'Hopital's rule. How do we actually prove this limit to be true? How can we prove it and make sense out of it? Let's talk about it. The purpose of this proof is for you to think beyond that rote procedure I just showed you, where you are just quickly and haphazardly applying the L'Hopital's rule to arrive at your answer, even if your answer is correct. How do we prove it? Consider this. When you're looking at that limit, theta as approaches 0, you're looking here at 0 from the right and from the left. This limit can in essence be simplified and represented as this. Limit as theta approaches 0 only from the right, and you're applying this limit only from the right, and your end result here will still be valid and legitimate, and your proof using that will still be legitimate. Why would that be the case? Well, you're looking here from the left hand side, what do you have? You're looking at negative values of that theta. Consider the fact that sine is an odd function. You would in essence be representing your test values on the left of 0 with negative, and then you would obviously put it here in the denominator too, a negative value. Since sine is an odd function, you know f of minus x is equal to minus f of x. In essence, you have minus sine of theta, because you can bring this out using the odd function property, over minus theta. These cancel out, and you are left with sine theta over theta, which means the negative values here suddenly become irrelevant. Only the positive side values are applicable, and you can convert this into a right-handed limit only and use that for your proof and for evaluation. This effectively becomes that, and that will be the setting stone for the rest of the video. Before I erase this, you know I've demonstrated you this fact holds true, and we will convert our limit to that, and you see the modification. Now let's have fun, actually prove it. You see the modification, the limit as theta approaches 0, your values from the right. Start here with an x and y axis, and the proof is rather interesting. You have here your origin, we'll label it as an O. Pick a point over here, we'll call that A. A certain angle from your x-axis, extend A, you can call this a ray, but we're not going to extend it infinitely. You have a certain angle theta. Find a point of equal dimension away. You see OA has a certain dimension. That OA dimension will be equal to a OB. And that point B can be right over here. OA is equal to OB, and we have here a sector created that AB is an R. You're looking over here at a sector. That sector over here is going to be labeled as AOB. I'm going to give here a rough value. OA and OB are equal to a certain radius, and that radius is equal to 1. Why would it be equal to a radius? Because if you were to extend this angle theta around a full revolution and you were to trace this point, you're generating a unit circle around your origin. We're just looking at a portion of that, and that portion is the sector AOB, the radius here being 1. OA is equal to OB, and these are your values with regards to the sector. What I will do now is, from this point B, I'm going to demonstrate a straight line down. It's going to be perpendicular to your x-axis. See, perpendicular. My segment here, that point being C, my BC segment will be perpendicular to OA. Okay? From this point C, we're going to generate another arc, and it looks something like this. I may have exaggerated a little bit over here, but you can understand. I curved it too much, and we'll call this point D. Actually, you know what? Let's fix it. Let's fix this and make it look more reasonable, and it won't be too curved, and it'll come right over here. Now you're seeing two arcs and a straight segment. What are these? I have an arc which is AB, I have another arc which is CD, and I have a segment which is BC, which is perpendicular to your x-axis. Now, because of these new additions, we have two sectors. I have my original sector AOB, but I have another sector COD. You need to see all of this because these are coming into your proof. These don't need to be shown anymore because you know what's a segment, what's an arc. I have a right triangle over here, and I'm labeling as that a right triangle. What is that right triangle? It's BCO. That's my right triangle. I need all of these because they come directly into the items I'm putting over here. If I were to look at the areas of these three items, two sectors and a right triangle, I know by this smallest sector, which is called COD in terms of its area, should be less than or equal to the right triangle, which is slightly larger, and that right triangle is labeled as BCO, which would be slightly smaller than the largest sector that is clearly visible to you, which was my original first item, AOB. Look at them. My AOB sector is larger than the right triangle, which is larger than this sector. I need to determine these areas because my limit will depend on those areas, and I can easily do so. I have right triangle trigonometry coming into play. Look, here's my origin point O, here's my point B, here's my point C, my certain angle theta. All of these three items, your large sector, your right triangle, the smallest sector, share that common angle theta. I know AO and OB are equal to 1. I have to determine CO. How can I do it? When I know OB is equal to my radius, which is equal to 1, I pointed these items out at the very beginning. I can easily do right triangle trigonometry, cosine and sine. If I were to do cosine of that angle theta, I'm looking at this adjacent, which is OC, over hypotenuse 1, which is irrelevant to even, right? OC is equal to cosine theta. If I were to do sine theta, I have here a opposite. That segment is BC over a hypotenuse which is equal to 1. So we know BC is equal to that, OC is equal to cosine theta. We don't need these items here anymore. I have everything I need now to look here at this in terms of the area. Area of the sector, which is slightly smaller than the area of the right triangle, which is slightly smaller than the area of the largest sector. What is the formula for the area of a sector? It's equal to half r squared theta. Let's look here at the smallest one, COD. This sector is COD. I have here a radius which is equal to what? OC. For this small sector, the radius is equal to OC, but it's also equal to OD. We haven't mentioned OD, but OD is equal to OC. If you run these items here through your sector formula, you have a half times the theta times that r square. What will that be? Half r square, which is a cosine theta square. Alright, that's cosine square theta, and then I have a theta. This right here is my area of that first sector, the smallest item here on the board. I'm looking here next at the area of the right triangle. Area of the right triangle is equal to base times the height. My base is an OC, which is equal to cosine theta. You have a half times base, which is a cosine theta. And then you have times the height, which is BC. We know BC is equal to sine theta, and we have that. The area of the right triangle is equal to cosine theta sine theta over 2. What's the area of the largest sector? You have AO as your radius or BO as your radius, and that's equal to 1. Half r squared theta, where r is equal to 1, you have a half times 1 squared times theta. It's just a theta over 2. I have now three items, three areas. Area of a sector, area of another sector, and an area of a right triangle. If I were to take all of these three items independently, divide them by a certain item, what is that item I'm dividing by? Cosine theta, theta over 2. If I were to take theta cosine theta over 2 as a denominator, a rational term, and divide each of these by that item, I can simplify them. When I simplify them, things cancel out. In this item, you'll be left only with cosine theta. You just do the division. Do cosine squared theta times the theta. You know, I can write this in a better way. I can bring that theta over and write this here. Theta over 2 cosine squared theta. It doesn't matter. Order does not matter when you're doing products. If you take theta cosine squared theta over 2 and divide it by theta cosine theta over 2, you'll be left only with cosine theta. And it should be less than or equal to this. Divide this entire term by this. Cosine theta over 2 cancel out. The only thing which is left is a sine theta over a theta, and that right there is your limit term right there. Sine theta over theta. Take that item here and divide it by this item. You'll be left with sine theta over theta, and it's correct. If you were to take theta over 2 and divide it by here, this theta over 2, this theta over 2, that cancels out. The only thing which remains is a 1 over cosine theta. Now you have these items. I have in essence taken these three areas and I've simplified them to these terms. This right here is the area of the smallest sector. This represents the area of your right triangle. This represents the area of the largest sector. Now we come through to the completion of this proof. If, as I have mentioned to you here, theta approaching 0 from the right holds, theta approaching 0 from the right, and now you're looking here at the evaluation in terms of cosine, because you're seeing cosines over here, and over here. We're going to squeeze the value in between. I'm looking now at cosine of theta. As theta approaches 0 or as theta becomes 0, we have equal to here. We are looking at cosine of 0, and you know that's always equal to a 1. This right here becomes a 1. 1 over cosine of 0 is a 1, 1 over 1. And then you're looking here at sine theta over theta is larger than or equal to 1, but it's also smaller than equal to 1. Therefore, it must be equal to 1 because it's squeezed right in between, and your proof comes to a completion. The proof is completed. We started here and modified our limit, made it a single-sided limit. We looked at 3 items starting from an original large sector, then we started working on that, and we generated a smaller right triangle, then we generated even a smaller sector. We looked at the areas of those 3 items. What you were looking here was this item, sine theta or theta, was effectively representing the area of your right triangle in between, squeezed between your 2 sectors, the large and the small. But each of those sectors tended towards 1, which means the item in the middle also tended towards 1 when the limit was applied. You would have done this over here by means of the limit application. Limit as theta approaches 0 from the right, cosine theta is equal to 1. And then you bring that in, then you have this item come through and your proof comes through to completion, and that right there is the end of it. Thank you for watching.